Hi, I'm Quinn, and today we're unpacking quantum error correction. So here's the thing. Imagine you're trying to build a sandcastle, but instead of working on a beach, you're building it during an earthquake. And instead of sand, you're using soap bubbles. That's basically what quantum computing is like. These quantum bits, or qubits, are incredibly fragile. A stray cosmic ray, a tiny vibration, even heat from the environment. Any of these things can completely destroy the information you're trying to work with. Now, in classical computing, error correction is actually pretty straightforward. If I want to protect the bit value 1, I can just copy it 3 times. 1, 1, 1. If 1 gets corrupted to 0, 1, 1, I can look at all 3, see that 2 say 1, and 1 says 0, and figure out that the original was probably 1. Democracy wins. Majority rules. Easy, right? But here's where quantum mechanics throws us a curveball. There's this thing called the no-cloning theorem. It's one of the fundamental rules of quantum mechanics, and it basically says you cannot make perfect copies of an unknown quantum state. You can't just photocopy a qubit like you can copy a classical bit. It's physically impossible. It's like trying to photocopy a rainbow. The act of measuring it to copy it destroys the very thing you're trying to preserve. So we have this paradox. We need redundancy to protect our quantum information, but we can't make copies. How do we solve this? This is where quantum error correction gets really clever. Instead of copying the information, we spread it. Think of it like this. Imagine you have a secret message written on a piece of paper. Instead of making photocopies, you tear the paper into several pieces and give each piece to a different person scattered across the city. No single person has the complete message, but if you bring enough of them together, you can reconstruct it. And if one person loses their piece, you can still figure out what it said based on the other pieces. That's essentially what quantum error correction does. We take one logical qubit, the information we actually care about, and encode it across multiple physical qubits. A popular scheme uses 9 physical qubits to encode just one logical qubit. The information isn't copied, it's entangled and spread out in this really intricate quantum state. Now here's the beautiful part. We can detect errors without actually measuring the qubit itself. We measure the relationships between qubits. It's like, okay, imagine you're in a dark room with 3 friends standing in a line. You can't see them, but you can ask questions like, are persons 1 and 2 standing the same distance apart as persons 2 and 3? You're learning about the configuration without actually measuring each person's exact position. In quantum error correction, we perform these syndrome measurements. We're checking, did an error happen? And if so, what type of error? Maybe a qubit flipped. Maybe its phase got shifted. We detect the symptom without collapsing the quantum information we're trying to protect. Once we know what kind of error occurred and where, we can apply a correction. We essentially undo the damage. The quantum information survives and our computation can continue. But I have to be honest with you, this is hard. Like really hard. We need those error rates to be incredibly low for this to work. Below a threshold of about 1% per operation. Above that threshold, the act of correcting errors introduces more errors than it fixes, and the whole thing falls apart. Below it, magic happens. We can, in principle, keep correcting errors indefinitely and run arbitrarily long quantum computations. Right now, this is one of the biggest engineering challenges in quantum computing. Companies are building bigger and bigger quantum computers, not just to have more qubits to compute with, but to have enough qubits to dedicate to error correction. Because remember, you're using 9 physical qubits for every 1 logical qubit. That's a lot of overhead. But when we crack this, and we're getting closer, that's when quantum computers will really take off. We're seeing different approaches compete. Shor's original 9-qubit code, Steen's more efficient 7-qubit code. And nowadays, the Surface code is becoming the favorite because it's more forgiving of the messy, imperfect hardware we have today. The Surface code arranges qubits in a 2-dimensional grid, kind of like a checkerboard, and it can tolerate higher error rates than earlier schemes, which is exactly what we need for real-world quantum computers. And here's the thing that gives me hope. There's this fundamental result called the threshold theorem. It's quantum computing's version of a promise. It says that as long as your physical error rates stay below a certain threshold, somewhere around 0.1 to 1% depending on the code, then adding more qubits and more layers of error correction will actually work. Errors get corrected faster than they accumulate. You can build up, scale up, and run computations that would take longer than the age of the universe on a classical computer. That's the foundation of fault-tolerant quantum computing, And that's the prize everyone's racing toward. So yeah, quantum error correction. Protecting soap bubbles during an earthquake by spreading them across space, measuring their relationships without looking at them directly, and trusting in a threshold that says physics is on our side. It's one of the most elegant solutions to one of the hardest problems in modern physics. Alright, let me leave you with the key takeaways. First, qubits are incredibly fragile and we can't just copy them like classical bits because of the no-cloning theorem. That's the core problem. Second, the solution is encoding. We spread one logical qubit across many physical qubits in an entangled state. We're not copying, we're distributing the information. Third, we detect errors using syndrome measurements. These special measurements tell us what went wrong without destroying the quantum information we're trying to protect. It's like diagnosing the problem without opening the patient. Fourth, different error correction codes exist. Shor's 9-qubit code, Steen's 7-qubit code, and the surface code, which is the current frontrunner for practical implementation. And finally, the threshold theorem is our reason for optimism. Get your hardware error rates below about 1% and error correction works. That's the gateway to fault-tolerant quantum computing and all the revolutionary applications we've been promised. That's quantum error correction in a nutshell. It's hard, it's elegant, and it's absolutely essential for the future of quantum computing. That's all for today. Take care.